Okay, so basically, it's going to be a quick overview of the state of quantum key distribution. I'm going to basically, I think we're going to cover some of the same ground, but from a slightly different perspective. What we have, and hopefully things that, at least from my research, we don't quite have yet. And then what organizations can perhaps do to get ready. We've already had a great first step there. But some practical smaller ways that you can get a little more ready. If you don't have a national initiative in place like I do. So we have a lot of the required parts, and it sounds like a lot of, and really everything is working very well as far as the technical parts. But I would, from my research, from what I'm seeing, every part that we have is only like probably 90% of the way there. It's there, it works, it's great, but it's maybe not quite enough to fully implement, right? Basically, what I'm saying is, no matter how you slice it, there's like two principal types of quantum key distribution. So there's quantum channel switching and trusted repeater sources. And there was a paper from the Institute of Physics that I think I saw mentioned in the last presentation as well. That was a big help for this. So basically, we've got two different ways of communicating, which are both very attractive in different ways. And I'm anticipating a hybrid approach. So I'm going to talk about both of them. Most schemes, in fact, I think all but like one that I'm aware of, use light, just because it's easy to create photons relatively. There's not much noise necessarily compared to other ways of doing quantum, and it's very easy to get them to move around. So the first way is quantum channel switching. I think if we can totally get rid of noise and decoherence and all that, this would be the easy way to do it. It's really just, you've got all these channels and you've got switches that just guide the light to where it needs to go. There's not much noise in light, but there is still some. And you're going to have more noise in like a fiber optic cable, been abused over time, even if it's well protected. Then there's also been research on running it through classical channels as well. And that's going to add more noise just because it's got other communication running through it that's different. There's also going to be impurities. It's moving a long distance. There's going to be lots of ways for it to react and change state. So to get around that, we have the other method of quantum key distribution, which is trusted repeaters. And it sounds like this is what most of the work is being done on. So basically, rather than amplifying or performing an extreme amount of error correction, there's the possibility we use these repeaters. Because amplifying is, in many ways, very hard on more or less single photons. So we have these devices which are able to continue to carry the information from point A to point B. There are two main methods here. The first is using key exchange hops. The second is using entanglement. In the first method, the hops, all the repeaters exchange different keys. This could be when a user initiates, or they're just constantly exchanging, just passing down keys down the line. They're all rolled together and passed down the line, and the combination is in the key. There seems to be the most algorithms here. It's probably less secure. One of the papers, I think it was from University of Illinois, was like, hey, we use this. We know it. The way we implemented it, at least, was not secure at all, but it will look the same. It looks the same from the endpoints we're looking at. Then there's the additional issue where some methods have classical data stored, which is going to weaken the overall security. You're going to have physical security, and whatever. Personally, I like the idea of leaving that one in the hands of the researchers, but it sounds like people are using it for satellites especially. So the second method uses entanglement to send the information down the line. I've got implemented in C or in Qiskit some examples of how that would be done. So actually on the right here is using what are called or swap gates. So basically you set your state. In this case, I just flipped it so it's easier to read over here. So this state is then moved from Q0 to Q1, Q1 to Q2, Q2 to Q3, and you can swap it from 3 to 0 as well while you're doing that. And you'll notice that it only ends up in Q3. It does not end up anywhere else. Then the other method is using CNOT gate. Basically, CNOT gates is just entangling the whole thing. Basically, just the first one's entangled, the second one's entangled, and so the second one is entangled with the first one, and so on down the line. It's not copying, but it in many ways can act like copying. So it's just, I feel like they have their different advantages and disadvantages. Like I mentioned, it requires trusted repeaters, which can be tampered with. They can be snooped upon. I saw research that suggested that just having a trusted repeater, we should not necessarily fully trust a trusted repeater. We should still question it. So I think that when it ends up that everything is settled, everything is implemented, when the technology is mature, we're going to have a hybrid approach. And that's going to depend on the density of nodes in the network, security and of the location, and a few other things, what is decided. For example, a network, if you're implementing it at a hospital, it could be a prime candidate for a channel switching network, since any two nodes are in pretty close proximity to each other. However, the relative density of access points could make it attractive to have the access points also be repeaters. So I don't think there's a strong bias either way, and it's just kind of, what do you need in this situation? Either could be attractive. And the struggle comes when there's a large difference between nodes, or a large distance between nodes. So like if there's a satellite office, so there's just a long distance between two nodes that's going through more or less public land.
Mark, I normally don't interrupt, but I think like this is really exciting. Just that I might be fielding some questions from the audience.
Yeah.
So are you saying, like, this seems very interesting. So we're talking about one way that basically we have a trusted repeater. However, we're introducing a physical security vulnerability. So we're losing that advantage of quantum because I can watch it. Whereas the other system, we're chaining entanglement, meaning fragile noise.
Right. Like
there's Am I getting this right? Yeah.
Yeah. I mean, that's one aspect to it. One of them is fragile. One of them, I mean, they're all fragile in different ways, I guess. So you can store a key in your repeaters and send through the channel and just have layers of encryption going through. That's fragile because you've got the physical,
we have a bit of a freeze, so this thing's happened. Let's see if anyone can message Mark. That system froze a little bit. Sorry about that, Mark. If you're able to hear me, if your presentation froze. Looks like you're good now. Be quiet.
Okay, cool. Yeah, so basically we're just fragile in two different ways, and you've got to make choices as to which one you use. So if that's all, I can continue.
Yes, please.
All right, cool. If you need more clarification, I can absolutely do that. So another factor is not just the physical hardware that you're using to move the keys around. You've also got how to get between the hardware. So there's two main ways, obviously, which is exact same as classical communication in this case. You've got fiber optic and you've got wireless. So they've got pretty much the same advantages and disadvantages as classical. So fiber optics, you can go around obstacles. You can possibly use classical and quantum information in the same channel. You've got a lot of options with this. It sounds like that a disadvantage is that you need an extremely high purity or a different mixture of isotopes and whatever in a quantum fiber optic cable. Just slightly different helps maintain the superposition and stuff a lot better. And then if you're doing things with classical data as well, you're also going to have problems with that's going to add noise. And then with wireless communication, exact same problems with wireless communication in classical. You've got, all the noise from who knows what between you and your target. So you want to minimize scattering. You want to have as much line of sight as possible. But I really don't understand. I've not been able to find a place that adequately explains to me how we can have, like, from what I see, the best way to do this is a single photon. How do you get that from the ground to a satellite or something? Because if it's more than a single photon, you can do a different set of attacks. That it severely weakens your communication there. So what the ecosystem still needs, I'm starting to get into that a little early. We definitely need trusted nodes. And there are a couple of ways it needs to be trusted. There's the typical cybersecurity, and then there's a little bit of an additional because it's quantum. We can't have downtime. If this is critical infrastructure, we either need enough redundancy that a little bit of downtime doesn't matter too much, or we can't have it. It needs to have a way to warn operators if tampering is attempted, and then resist it for as long as possible. Lastly, the technology itself needs to be trusted. This one's a little bit interesting because like, we are moving with quantum key distribution, we are moving from a place where we are using the same kind of ideas as we've been using since written history, and moving on to just a lot of new stuff. This is new, well, not new physics, but it feels new, and it's something completely different. So it's got to be trusted, and as far as the technology is trusted, it's got to be trusted as in we can trust the physical implementation. So yeah, we need a lot of work here because around the communication especially. And we need to be able to protect these trusted nodes, which might actually be a lot easier with satellites, which is a very interesting thing that I've not had a chance to look into, because I've been this is an overview. So we also need like non-measuring amplifiers.
So this is very interesting. I'm sorry to interrupt because we need
Yeah.
to start moving things forward for Steve Hollins, but
Okay.
this is very interesting. So you're mentioning though, like the trusted node is a satellite, and that looks like something that actually we've got an expert here. She's not presenting right now, but Anna Bieta, right, with their company Quantum Prime. It looks like that's a very big signal that
Yeah.
could be of extreme utility. And
Yeah.
Mark, what I would add is I would hope that that becomes more of a threat in space by more humans being out there. That would be
Yeah.
kind of a good, bad thing. Anyway,
Yeah.
so to wrap this up for the next couple minutes, because we're getting ready for Steve to launch, what would you say in conclusion to wrap all
In
this up?
conclusion, like, yeah, I apparently went a lot slower than I did in my practice, but
It's no worries, no
okay,
worries.
so
It's information dense, and I think really like what you're presenting here takes a little time to percolate and digest. So no worries.
yeah, so basically, I would say with all of that, what you're going to have to do and what you're going to want to do is you're going to want to start out by looking at the standards in your country. So the NSA is like, no, let's not do this. Because you've got all those risks and stuff, and it's only a partial solution on all that stuff, sort of thing. And so that's your first step is you're going to have to understand that, and then if you've got to have it, you've got to probably start building it out on your own, because the most utility you're going to get to start out is being able to communicate within your organization and then have a way out. So, satellites or national initiative or something. So it's just going to have a lot of money to go into it, basically. And so you're going to want lots of money. You're going to want to develop your local network for your organization and then have plans. And if there's already one implemented for a wider network, prepare for that and do that if it's available.
All right.